now we come to the special cases of the equilateral triangle, which is sort of the most beautiful figure in geometry because it's the simplest. So equilateral triangle is 60-60 each angle, like everybody would be knowing that obviously, but yes, the important thing is that for equilateral all 4 points are the same. So this point will be H, G, O, I. All points will be the same point. So like in center, circumcenter, centroid, orthocenter. All points are the same point. To say that basically that okay, if you like whatever definitions we have discussed, right? So all of them relate to the same point here. For example, for in center, we saw that okay, this is the in center. Now for an equilateral triangle, the same point will be circumcenter. So for example, if you draw a circle here, it is circumcircle. So the same point will be the circle, will be the center of both this circle and the big circle because it's both the in center and the circumcenter. Similarly, if you draw the medians, they will meet at this point itself. In the same point, this one. This will be a centroid as well. If you draw perpendiculars, it will again meet at the same point. It's the orthocenter as well. So the most simplistic construction that is possible is the equilateral triangle. Right. Now talking about the equilateral triangle, right? So there are a few formulas here which we derive and sort of avoid memorizing as such. The area obviously is very common, root 3 by 4a square. So that is like every side is a. So this is like everybody knows, root 3 by 4a square. Now, what is the circumradius and the inradius for this? It's always good to keep that in mind, but we'll also derive this just so that if you're confused or you know you're sort of not able to recall, then you can easily derive it in one line. We know that area of a triangle, which is this one, is equal to ABC by 4R from the previous slide, right? So area is this much, and ABC here will be A cube because B and C are both equal to A as well, and divided by 4 into R. So 4 gets cancelled, and A becomes, or R becomes, A upon root 3, which is the circumradius of an equilateral triangle. Easy to write just using ABC upon 4R, and the circumradius is A upon root 3. Let's talk about the inradius now. We know that inradius is area upon semi-perimeter. Area is root 3 by 4a square. Semi-perimeter here would be a plus b plus c by 2, but a plus b plus c would be 3 times a because it's an equilateral triangle, so it will be 3a by 2. And this actually gives you a upon 2 root 3. So for any equilateral triangle, the circumradius would be a upon root 3, the inradius would be a upon 2 root 3. So like to say that okay, inradius is half of the circumradius essentially. So basically, if you draw, like if you see from this standpoint, then this radius would be half of, let's say, this capital R. So this would be a by 2 root 3, this would be a by root 3. The other relations still hold, like the 2:1, etc. Like again, this point it will divide this line into 2:1, etc. Because again, this point you can treat it as median, centroid, and center, circumcenter, whatever. So this is one. These are the two relations that you should know for also for equilateral triangle, right? Equilateral triangle is beautifully symmetric in other ways as well. For example, in an equilateral triangle, there are some interesting relations that kind of make it simple to operate here. If there is any point, okay, let's first talk about the height of an equilateral triangle. Right? If you talk about the height of this, you can find the height of this. This will be, the height is the same as median, because for an equilateral triangle, the altitude is the median, is the angle bisector, is everything. So altitude will be the same as median, will be the same as angle bisector, and everything, right? So height you can find out. This is A, this is A by 2. So height of an equilateral triangle will be A root 3 by 2, direct Pythagoras. Right, and so this is the height. The application of the height is if you take any random point in a equilateral triangle, let's say this point, P, right, and you draw perpendiculars, like you measure the distance of P from the sides. This is a perpendicular, this is a perpendicular, this is a perpendicular, let's say PM, TN, and distance in geometry will always mean like a perpendicular distance, right? So if we say that, okay, from this point, this, how far is this point from this line? So you will draw a perpendicular in general. So if you want, if this is an equilateral triangle and if there's an internal point P and you sort of measure its distances from the side, the perpendicular distances, the sum of these perpendicular distances, PM plus PN plus PT, will always be equal to the height of the triangle, which is A root 3 by 2. The name or the theorem is not important, that's why I'm not naming it, but yeah, just in general. So like if they ask like, okay, there's an equilateral triangle and like line segments are drawn from an internal point to the sides, or maybe like there's a person inside this equilateral triangle. So what is the sum of his distances from this side, this side, this side, etc. Something of this sort. So the sum of those distances, irrespective of wherever the point P is, if it was P here as well, then the sum of the distances like this plus this perpendicular distances would have been equal to A root 3 by 2, which is equal to the height basically. So that is there. That's one relation. This distance, the distances, yeah, the PM will perpendicular. Like whenever in geometry we say, even if it's a general triangle, right? So if let's say somebody asks you that, okay, how far is point M from side AB? Right, the answer will always be the perpendicular distance from M to AB. Like it's not like you can draw any line from M to AB and then call this the distance of the point from the line.
Okay.
So this perpendicular distance gives you this relation.
Okay.
So that is it. From an equilateral triangle standpoint, you can also have a relation from like how far are these from the vertices. So for example, like this was with respect to sides, right? If you have an equilateral triangle, let's say this one, and you any random point, let's say P, and you draw, like you connect this P to the three vertices, the sum of these three distances will be equal to A root 3, is half of this basically. So like let's say you have the point P here, you join it to the three vertices, mark it as X, Y, Z. So the X, Y, Z, like the lines to the three vertices will sum up to A into root 3. So this will be equal to the height and this will be equal to A root 3. This is actually not necessary, like this is like as in, okay, this is necessary, it will always hold true, but in general, this is not asked like in question. This like comes of use at some point. So this is the stuff for an equilateral triangle, right? Now coming to the other special case, which is the right triangle. Right. So as we covered that the midpoint of the hypotenuse will be the circumcenter of this. So to say that, okay, if let's say this is A, B, C, so this is basically A, this is basically B, this is basically C. So this will be B by 2, B by 2, and this is the circumcenter. We just covered this, right? Similarly, this would also be B by 2 because circumcenter is equidistant from the vertices, right? So if you draw a triangle, basically this will be the radius of that circle. So this is the first important point in terms of the centers around the right triangle, and this was the orthocenter as we mentioned, right? That the vertex of the 90 degree is the orthocenter in case of a right triangle. The other relation in terms of a right triangle is that the in radius of a right triangle is A plus B minus C by 2. Actually, let me just redraw this figure once. This would be A, this would be B, and this is C, the hypotenuse. So for this triangle, the in radius would be A plus B minus C whole upon 2, which is the legs of the triangle minus the hypotenuse whole half will give you the in radius. And we know that the circumcenter is the midpoint of the hypotenuse. So the circumradius, capital R, would be C upon 2. Right? So the circumradius, as in if you draw a circle, then the radius would be that one. So it is the half of the hypotenuse C upon 2, and R is this. This is always true for a right triangle. Right. So basically, if you add both of these, you will get R plus R equal to A plus B by 2. So sum of the in radius and the circumradius is half of the sum of the legs of the right triangle. So this is one relation. The other relation is that for a right triangle, the area is equal to R into small r plus 2 times capital R. This is important. Actually, all these relations are sort of important only. So yeah, this, okay, still you can derive from the above two, so not really to remember anything here, but this needs to be remembered. This is anyway the sort of a definition itself, so like this anyway needs to be kept in mind. But yeah, the area, like it can directly come of use, that okay, this is the in-center, this is circumcenter, what will be the area of the triangle? So you can say that small r into small r plus 2 times capital R. For example, if the in-center is given as 8, the circumradius is given as, let's say, 20, so the area would be 8 into 8 plus 28, sorry, 8 plus 40, so 8 into 48, whatever this is. So this is regarding the right triangle. And again, we just discussed also, right, that in a right triangle, if a perpendicular is drawn from the right angle itself, then we just saw that, so CP square equal to AP into BP. This into this will be equal to CP. So this is, so this basically sort of encapsulates what is important from a right triangle standpoint. Yeah, now let's move on to some other basic properties of triangles, right? So, and deliberately, I was discussing this because sort of it's easier to do it earlier in the session, because it helps to ensure that level of focus as well in the beginning. Now, coming to the concept of the area of a triangle, now there are many formulas around this. Let's just list them down. First is half base into height, really like the school years formula, right? Nothing much going on here. Base height, half base height, done. Second is half AB sine A or half BC sine, half AB sine C or half BC sine A. Again, this refers to our standard diagrams of A, B, and C. Half AB sine C would be around this, BC sine A around this, sine B around this. Right, and so all these three represent the areas. The third, the famous one again, is the Heron's formula, which is square root of S minus A, S minus B, S minus C. S is A plus B plus C by 2. Fourth is using the in radius, as we again discussed, which is area equal to in radius as in R into S, where R is in radius, S is semi-perimeter. The fifth, as we saw, that for a right triangle, the area was R into R plus 2R. Right. Now, all these are expressions depending on what parameters you have available. Again, of course, there was another one. Let's just write it for thing. A, B, C, where 4R is also area. R is circumradius. So there are like half a dozen formulas for area. And like if you're given coordinates, there's a separate formula for coordinate geometry as well. But the point is that whatever parameters you have available, you have to use a certain area formula to sort of get the area based on those parameters. So for example, if you're given the in center, you need to look at this one. If you're given the angles, etc., and all, then these ones will be there. But actually, the simplest formula of all, just the half base into height, has a certain nuance to it. Let's just discuss that and how it can be used powerfully, actually. Right. So, for example, if you have a triangle here, let's say, right, or actually both this and this have, like, these two seem to be the simplest formulas, but there is a nuance to it, which is this one. So, for example, if you have a triangle ABC and you have a point D, now there are two triangles here, like ADB and ADC. Right. For example, if the base lengths are in a ratio A is to B, right? So for example, BD is to DC is A is to B. Then the area of these triangles will also be in the ratio of A is to B. So triangle ABD by triangle ADC will the areas of them will also be in the ratio of A is to B. Why and how? See. What is the area of triangle ABD? And again, understanding it is always safer, just in case you're not able to recall. So the area of ABD will be half A into AD times. So if this is, let's say, X and Y, the ratio, so BD by DC equal to X and Y. So the result is that the area of triangle ABD over triangle ADC will also be X and XYY. How? What is the area of triangle ABD? It will be half into BD into AD into sine of this angle, BD, AD, and the sine of the included angle. So let's say this angle is theta, so sine theta. And what is the area of triangle ADC? Half CD into AD. AD is common in both triangles, so AD features in both. Sine of, what is the angle here? This is 180 minus theta, and this is what we have to take. We know that sine theta and sine 180 minus theta are the same thing. So when you divide these to find the ratio, these get cancelled out, AD gets cancelled out, half gets cancelled out, and you're remaining with BD upon CD, which is the same ratio. So this is how you get the result, but it's a very powerful result that the ratio of areas of two triangles will be the same as ratio of their bases. We'll look at a couple of questions when we get to the questions as well for this. Right, so for example, if this is 3:4, then the ratio of this area by this area will also be 3:4. This is like from a naming perspective, it's called the base area theorem or the base area ratio. So this is important. Okay, so in terms of area, the only other thing is that for an equilateral, we saw that the area, let me just write it again, is root 3 upon 4a square. For an isosceles triangle, again, all like you can always find the area by Heron's, right? But sometimes that gets a bit calculative. If you are given the sides, for example, if an isosceles triangle, if this is 3, 3, and 4, for example, right? You can always apply Heron's to get the area if the sides are given. But whenever you see that it's isosceles, it's always good to sort of have this shorter formula, which is the formula is b upon 4 root 4a square minus b square. This helps to calculate it very quickly. B is the different side and A is the same side. So in this figure, A will be 3 with the same side and B would be 4. So the area here would be 4 by 4 root over 4 into A square, so 4 into 3 square, 4 into 9, 36, minus B square, so minus 16, so which is root over 20 or 2 root 5. So it's a much quicker way than Heron's will also give you the same answer, but just to save time, this is the formula for an isosceles triangle: b by 4 root 4a square minus b square. So now that we've covered this, right, let's move on to the next bit in this, which is, and again, like please feel free to ask any question or stop me at any point if you feel that something's not clear. The next topic is similarity. Pretty sure you would have all studied this, and it's just basically that there are two rules to keep in mind here. So if any two angles are similar, so if this is theta, this is theta, this is alpha, this is alpha, those triangles are said to be similar by double A rule. And the naming is important because that will dictate how you put that equation for the sides. So in this case, for example, ABC is similar to what triangle? So A we cannot comment because we don't know like what angle A is equal to here. B we know alpha is same as alpha. So in place of B we'll write R. The B was in the middle, R will be in the middle. C is theta, which is P. So in place of C there will be P and the remaining one would be Q. So these two will be similar. So if you had to write the side ratios or in order to find the sides, it will be AB by QR, the first two of this, equal to BC by RP, last two, the first and a third. And this you can use to find unknown sides and stuff. So this is the AA rule. or the triple A rule, because obviously if two are equal, the third will also be equal to the other. The second is the SAS rule, which has a small detail to it. It's the same two figures essentially. Now, this basically says that if the side ratios match, then the triangles will be similar. So, for example, if we are given that AB by PQ is same as AC by PR, and this, like, if we are given that this is true, and the included angle, please note the keyword here is the included angle. So, for example, if the given ratio is with respect to sides AB, PQ, and AC, PR, so the included angle would be this one and like PQ and PR, PQ, PR, so then this one. These two angles need to be equal, and which is very, very important. The word included angle is key here. Right. So, for example, if you were given that, okay, this is theta and this is theta, and this ratio was true, would the triangle be similar? No. You need the included angle to be equal. This needs to be theta for the triangles to be similar. Yeah, so this needs to be theta, so this needs, the included angle needs to be equal. What do I mean by included angle? So the sides which ratios are given, like here the ratios are given as per AB and AC of this triangle, AB and AC, or PQ and PR of this triangle. The angle that is contained between them, those need to be equal. Then only you can say triangles are similar. So it's always a good check to see that what sides are proportional. Right. So this is similarity. Again, if the triangles are similar, like, okay, this is sort of to like gauge whether two triangles are similar or not. If they are similar, then the sides are in the same ratio. So, for example, if two triangles are similar, then AB by PQ will be equal to AC by PR will be equal to BC by QR in that ratio, right? And they will, like, so if this is like 1:2, if this is given 1:3, then this would also be in the ratio 1:3. So if this is 2, this will be 6. If this is 4, this will be 12, and so on and so forth. Right. So that is the one. The ratio of areas would be the square of the ratio of sides. So here the ratio of side was 1:3. The ratio of areas would be 1:9. The ratio of areas is always 1:to side the whole square, like the ratio of side square. Okay. So for example, if the sides were in the ratio 3:4, the areas would be in the ratio 9:16. That's just it. And this would come of use actually. And so this is the, like, this is with respect to what the impact of similarity would be. Now, how do we, like, okay, if somebody tells you or asks you that, okay, are these two triangles similar, you would be able to easily gauge, right? You will compare the angles. Okay, even if the angles are not equal, you will compare the proportion of the sides and then see that, okay, if there is some proportionality, the triangles would be similar, and if the included angle is equal. Okay, but in questions, how do we know that similarity has to be applied, right? Okay, before we get to that, there's one small nuance that needs to be mentioned here. Again, something that people remember from similarity is that the ratio of sides is same. So this by this, or something like the ratio of side would be 1:3 for all the pairs of sides. The people remember that. People remember the ratio of areas. What people do not remember generally is that if the two triangles are similar, then the ratio of sides will be the same as ratio of heights. So heights will also be in the same ratio, will be the same as ratio of in radiuses. Like all the parameters that we studied, right, those will be in the same ratio, will be equal to ratio of circumradiuses. So if two triangles are similar, so side ratios obviously, like, people would realize it's the same, but that the even the height ratio, the in radius ratio, and the circumradius ratio will also be the same, right? So if this is like 1:3 in this case, or let's say if the side ratio is 3:4, the ratio of in radius of those triangles will also be 3:4. The ratio of circumradius will also be 3:4. Only the ratio of area would be the square. Okay. So now coming back to the point of how do we know that in a particular question should we start looking at similarity or not, right? Because typically questions obviously won't tell you, right? And this is the major catch in geometry as to how to strike questions faster. So now how to know where to apply similarity, right? Like what is the hints in the question? The first hint usually is parallel lines in the diagram. And this, like, if you have any setup with parallel lines, for example, you have the circle and this is parallel to this. So basically, if this is parallel to this, then we know that this angle will be equal to this angle, corresponding angle, this angle will be equal to this angle. So these two triangles will be similar, the small and the big one. So triangle APQ will be similar to P is same as B, Q is same as C, so will be similar to ABC. Okay, so parallel lines, you should, like, whenever there's a figure, so you should start thinking in terms of, okay, like, is there some relation, some similarity that we can use? It's not mandatory that similarity will be used there, but similarity would definitely be one of the potential options to use in case the question asks for that, right? In fact, you also have a theorem around this, like not a theorem per se, but just as that if it's a triangle ABC and you have a line parallel to the base, and this is parallel to BC, so these two triangles will be similar as we've just discussed. This angle same, this angle same, common angle similar. Definitely, this whenever there is parallel line, there will be similar triangles, right? Even if I extend this to another bigger triangle and say that okay, this is parallel to PQ, so basically it is MN parallel BC parallel PQ. So all the triangles will be similar. Like this will be similar to this one, this will be similar to big one, this will be similar to the big one. The ratios will vary, of course, but all the triangles will be similar. So any relation you can write and use depending on like what is asked in the question. So the result is that basically that if you join the midpoints of the two sides of a triangle, so if you join the midpoint of two sides of a triangle, it is parallel to the third side and half of it. Right. So basically, if this is the midpoint of this is the midpoint of FM and N are the midpoints of AC and AB respectively, then MN will be half of AB. Only if it is a midpoint. And MN will be parallel to AB. Parallel to AB. So this is called the BPT or the basic proportionality theorem. No, it will always be necessary. If you are connecting the midpoint, they have to be midpoints, then see it will always be parallel, and if it is the midpoint, it will be half of the third side. So MN will be equal to half of AB, and MN will be parallel to AB. If you are joining the midpoints of, so for example, if you have a, let's say, and this will be true for all triangles. So for example, if you have this one, right, if you join the midpoint of these two sides, for example, this is the midpoint, it does not look like it, but let's say this is the midpoint of this side, this is the midpoint of this side, and then this line joining them will be parallel to the third side and is half of it. Maybe this would appear parallel to the third side and is half of it, and this will always be true. And any parallel line will create similar triangles. They don't even need to be midpoints. So for example, here it wasn't this line wasn't the midpoint, but parallel lines will always get similar triangles. Right, and this is the result for the basic proportionality theorem, that if the midpoints are joined, then the only additional thing is it would be half of the third side. So this is a midpoint, this would be half of the third side. Now what does this tell me? That okay, if this is half of this, then this will be half of this by similarity, and this will be half of this by similarity. So basically I know from BPT, basic proportionality theorem, that MN is half of AB. So by similarity, CM will be half of AC, CN will be half of BC. Side ratios will be 1:2 in the small triangle and in the big triangle. So if side ratios are 1:2, what is the area ratio? 1:4. So basically this area over the whole total area is 1:4. How did I get to it? The side ratio was 1:2. There used to be like, they don't ask it nowadays, but there used to be this thing that okay, if you join all the midpoints in a triangle, all the three midpoints, what is the ratio of this area to this to like the overall area? Okay, so if we try to address this question, right? So we know that okay, and these are all midpoints. So BR equal to RC, CQ equal to AQ, BP equal to AB. These are all midpoints. And again, if these are midpoints, then by BPT I know that PQ will be half of BC, PR will be half of AC, and RQ will be half of AB. And also these will all be parallel to these sides. PQ will be parallel to BC, PR will be parallel to AC, and so on. So because they are parallel, once again, it means there will be similar triangles that are getting created. So this triangle APQ by ABC will be 1:4. As we just discussed that if the side is half of the big triangle side, the area will be 1/4. Similarly, this triangle, the side triangle PBR will be also be 1/4 of ABC, because even here the side ratio is, this is half of this side is half of this again by BPT. So the area of this by area of this big triangle would be 1/4. Similarly, CQ will be half of not CQ, like this one, QR will be half of AB. So again, CQR will also be 1/4 ABC. So this will be 1/4 ABC, this will be 1/4 ABC, this will be 1/4 ABC. So the total they sum up to 3/4 of ABC, and so this again will be remaining, will be the 1/4 of ABC. Yeah, this is true for all. You could have derived it directly as well. Like even if you take this triangle and the big triangle, even here the side, if you see this small triangle sides, so A side, this side is half of BC, this side is half of this side is half of this. So you know that the side ratios are 1:2, the area ratio is 1:4. So you don't even need to calculate the areas of these three individuals, but just did it to illustrate this principle. But again, long story short, whenever you see parallel, that is a good indication that okay, it might be possible to apply similarity if the question requires something that needs similarity. Right? You will actually see these. You would have actually seen this some diagrams that are relevant here, right? So, for example, again, I know this section is for triangles, but even if let's say for circles, we say, right, you would have seen figures like these here and joined here or something like this, right? Very common setup, really. So these are the centers of the circles. This is R, small r, this is capital R, or R1, R2, whatever. Right, and if you join here, again, since this is parallel to this, and how do I know this is parallel to this? Both are perpendicular, radius perpendicular, tangent. So both are perpendicular, so this will be parallel to this. Again, this triangle will be similar to this triangle. If the rate, so and everything will be in the ratio of the sides then. So R by R will be equal to this. So basically, if I was to write an equation for this, this is P, this is Q, and this is R and R. So once I know that okay, this is parallel to this, these two triangles are similar, so all the sides will be proportional and in the ratio of R is to R. So if I'm given the ratio of radius, here is, let's say radius is 2, here radius is, let's say 5. So the side ratio is 2/5. Triangle APQ is similar to triangle AQC. This is similar to the whole triangle, and the side ratio is 2/5. So which means that all the side ratios will be 2/5. So for example, if I write AB by AC will also be 2/5. This by whole is still 2/5. AP by AQ will also be 2/5. And similarly so on and so forth. Again, an application of similarity. Right. There's another this thing, and it used to be like, not used to, like basically there was a word problem around it, that there is a like there is a straight wall or something, or a ladder, whatever, and there are kept at two ends here and here. This is the ground. There are ropes tied to the top of this, and rope, not actually this one. Let me. Yeah, so one is connected to the foot of the next foot of the other. So for example, this is connected to the foot of this, this is connected to the foot of this. So they used to ask that, okay, how high above the ground is the meeting point of the two ropes? So what is this height essentially? Again, a similarity result that is used. And why similarity? Like, or how do I know it's similarity? Because again, this is parallel to this, and these two are parallel to this. So once I know that they are parallel, right? So again, in this triangle, if we see this and the big triangle, so triangle DPD, similar to what? And again, just to reiterate once again, and cannot stress this enough, that the naming is of utmost importance here. So in this triangle BPD, I know that they are similar because like angles like created by parallel lines, like corresponding alternate angle, etc., would always be equal. but to name it carefully is the point here. So BPD and this big triangle, right? So obviously B and B is common. So where B is coming here, B will come here. Now P is 90 here. So we'll have to look at what is the 90 in the big triangle. So 90 is this. So in place of P, there will be A. And in place of D, whatever is remaining, there will be E. So let's say if this is on this side, this side is Y. So this triangle is similar to this big triangle. To say that basically if we write BP by AB, like side ratios, is equal to BD by BE is equal to PD by AE. Okay. So now again back to our question of okay, what will this height be essentially? So again, this height is PD, right? So we can write PD as H. Now we can use basically, like for example, we can use any, and similarly if these two triangles are similar, even these two triangles will be similar by the same logic, right? ADP and ABC, this one again parallel lines. Why? Because this is parallel to this is straight line first, and this is parallel to this, so again the angles will be equal. This angle will be equal to this and this angle will be equal to this. So by double A rule, these angles will be similar. So triangle ACD similar to triangle ABC. So again, even from here, you will have the relation of PD by BC equal to, let's say, AP by AB, right? And PD again is H basically, which we needed to find there, and BC again is Y basically. A here was X. So H by X from here is equal to BP by AB, and H by Y from here equal to AP by AB. And you can use this to sort of come up with a relation for H. So let's just continue it here. Basically, if we add these two, right, H by X plus H by Y will be BP by AB plus AP by AB. BP plus AP is nothing but AB itself, so this is equal to 1 actually, because BP plus AP is equal to AB, and AB by AB is 1. So H by X plus H by Y equal to 1. So basically you can derive H from here will be XY over X plus Y. So this is basically XY upon X plus Y. Again, no need to remember at all, but just to again show the application of similarity here. It's just a good example to, right? So this is one application of like how to find similarity, because you will find these parallel lines cases coming up. The next hint of using similarity is if the question gives two angles as equals in the diagram. So if you, for example, have a random diagram, right, like this or something, and they give, let's say, this theta equal to this theta, then it should strike you that maybe similarity can be applied, right? Again, obviously, one pair of angles more needs to be equal, or the side need to be proportional, but at least it can get you started on that line of thought that, okay, if angles are given as equals, can I prove them to be similar? So to prove them to be similar, you'll either have to prove another set of angles as equal, or you'll have to sort of like prove that the sides are proportional. Right. For example, if let's say, and this also used to be a common diagram, let's say you have a right triangle and you have a square, for example. This is a square inside a right triangle, right? And let's say you're given this, and you're asked the length of this entire AC, like what will be AC equal to, right? So how would we sort of go about this? We know that 3 and 4 is given, so this will be 5. So side of the square, and it's given that it's a square, so all sides are equal, and the vertices are at 90 degrees. So 5, 5, 5, 5, and this is 90, right? So now basically, if we see that if this is square, right? If we draw a line of this, and we need to find the length of this, right? So if we draw a line here, and this angle is given as 30 degrees, right? If we draw a perpendicular line here, right? And we call this angle as theta. So how much will be this angle? The sum of these three will be 180. This is 90. So this will be 90, and this is theta. So this will be 90 minus theta. So this is theta. This is 90. This is 90 minus theta. In this triangle again, this is theta. This is 90. This is theta, and this will be again 90 minus theta. So this again is 90 minus theta. So again, in these two triangles, essentially, I've proven that two angles are same. One is, this is 90, this is right triangle, and this is 90. So these two angles are equal. Also, this is theta and this is theta. So this also is equal. This angle and this angle is equal. So this is actually theta, not 90 minus theta. Let me just draw. Let me just basically put in the triangles of different diagrams. So this is theta, this is 3 and 4, and this triangle was right. So again, these two triangles are similar. Now, how do we name them? Let's say P and this is R. So triangle, and this is M. This is N. So AMP, in AMP, similar to triangle, how do we name this? M and R. So A is 90, so it has to match with the 90 here, which is N. M is theta. M has to match with the theta here, which is R. And the remaining will be M, which is this one. So to say that basically that AM by NR will be equal to AP by MN and will be equal to MP by RM. Right. Now we know that in this relation, again, the natural next step to this writing this relation is we have the equation now. So we can find sides. So where do we have maximum things given? Like here we know that the side of the square is 5. So MP we know is 5. MR we know is 5. Both are sides of the square. So this is 5, this is 5. So this ratio, all these ratios will be equal to 1. To say that basically AM will be equal to NR. Right. So AM equal to NR. AM we know is 3. Here. So NR would be 3. We know 3. We know this is 30. We can find this length, and we can use AP equal to MN to find this. AP is 4, so this will also be 4. So we have 3, we have 4, and this we can find by using actually cot 30, which will be equal to CN by 3. So CN is equal to 3 root 3. So the entire length of AC will be nothing but 3 plus 4 plus 3 root 3, 7 plus 3 root 3. If it was given that, okay, this is an isosceles right triangle, then you could have even found out the area, because isosceles area means that, okay, this side and this side will be equal. So you can just basically write half into AC square will be the area. AC you just derived. If it was given that it was expressed. Otherwise, they'll give something if they want to find the area. But like again, this is again an application where we didn't know from the question data that, okay, two angles are equal, but we were able to prove that two angles will be equal. Even when there were like no, like as in parallel lines were not there clearly, right? So we figured out that, okay, these angles will be equal using like the normal angular properties. And so we were able to figure out that, okay, the triangles will be similar. This is there, and similarity again we'll again re-explore when we come to questions, because that will actually throw much more light onto